Let us consider the case of alpha chloropropionic acid and beta chloropropionic acid in a little detail. Now, in the case of alpha chloropropionic acid, there is a methyl group which shows a plus I effect. Now, the alpha carbon here gets delta negative charge. And again, chlorine shows a strong minus I effect because it is more electronegative, and the alpha carbon possesses a delta positive charge. Now, the magnitude of delta positive is greater than delta negative, so this carbon, alpha carbon, still possesses a partial positive charge. Now, due to resonance of the carboxylate group, we get a delta negative charge on oxygen atom of the carbonyl group and a delta positive charge over the oxygen atom of the OH group. Now, here one more effect operates, that is hyperconjugation from the CH bond shifting in this direction and CO bond shifting in this direction, so that the negative charge, partial negative charge over this oxygen atom will be slightly higher than in the case of formic acid. So, this negative oxygen, delta negative oxygen, will show a plus I effect where the electron density or electron pair shifts occurs in this direction, and when it comes to this carbon, it is a junction where the electron flow is divided between these carbon-carbon bond and this carbon-oxygen bond. Already it is having a partial positive charge. So, and the chlorine is more near to the alpha carbon or the carbon chain here. So, a major part is driven to this oxygen atom, and more or less same fraction is given to this carbon chain. So, there is almost equal division of the electron density flow by inductive mechanism towards this direction and towards this direction, since chlorine is more close to this carbon and this oxygen. Now, the inductive effect of a methyl group may be neglected at this point because it will be delta negative here, and it will be very small in magnitude. So, the inductive effect of delta negative oxygen will be shared between this chain system and this oxygen. Almost equal sharing occurs here. And so, the oxygen atom of the OH group will be still having a substantial amount of positive charge, so that it will show a greater tendency to take up the electron pair in the OH bond, increasing its acidity. In the case of formic acid, here for the whole group, instead of this whole group, we are having hydrogen, and almost all the electron density by inductive mechanism will flow to this oxygen, whereas in alpha chloropropionic acid, due to the minus I effect of chlorine and the partial positive charge still present on this alpha carbon, a substantial portion of electron density flows in this direction, so that the electron density flowing towards the positive oxygen will be less than that in the case of formic acid. So, formic acid is having a pK value of 3.751, whereas alpha chloropropionic acid is having a pK value of 2.84. A lower pK value indicates high acidity, And so the high acidity of alpha chloropropionic acid over formic acid is mainly due to the position of the halogen and its strong minus effect. That is the main reason. It is more close to the carboxylic acid group because chlorine is on the alpha carbon. When we come to beta chloropropionic acids, the most important point here to be mentioned is the hyperconjugation involving the CH2 group and the CO group here. These two CH bonds are alternate to the pi bonds or double bonds between carbon and oxygen. So, two hyperconjugation canonical structures can be written, and these hyperconjugation canonical structures will increase the negative charge over the carbonyl oxygen. So this delta negative will be greater than this delta negative. And again, the partial positive charge over the carbon adjacent to the carboxylic acid group is delta positive, because chlorine here acquires a delta negative charge due to its minus effects, and the carbon directly bonded to chlorine acquires a delta positive charge. And the next carbon, here it can be called the alpha carbon. Alpha carbon acquires a delta positive charge. So the inductive effect of delta negative oxygen will be transferred at this junction to this carbon chain and towards the oxygen atom. The share of inductive effects transferred to this carbon chain will be less, because one thing, the alpha carbon possesses only a delta positive charge, and the chlorine atom which shows minus effect is far away. So that a major portion of electron density will be transferred to the delta positive oxygen, and this portion transferred to the delta positive oxygen is greater than the partial negative charge or electron density shift in formic acids. And here the delta negative charge here is having a higher magnitude than the delta negative charge in formic acid, and that is due to hyperconjugation in the molecule. So hyperconjugation is an important aspect here, which will increase the electronic charge, delta negative charge over oxygen atom of the C double bond system. So that the electron density around this oxygen is greater than that in formic acid and alpha chloropropionic acid, so that this oxygen atom will be showing a lesser tendency to absorb this pair of electron to remove H as H positive than the OH group in alpha chloroacetic acid or formic acid. So beta chloropropionic acid, this is alpha and this is beta. Beta chloropropionic acid is having a higher pK value of 3.992, which is greater than that of formic acid and that of alpha chloropropionic acid, increasing its acid strength. So when we compare formic acid, chloroacetic acid, alpha chloropropionic acid and beta chloropropionic acid, once again formic acid, there is no group which withdraws or injects electron density into a group, so that the negative charge, partial negative charge, induces the complete electron density towards the delta positive oxygen by inductive mechanism. When we come to chloroacetic acids, there are two hydrogen atoms which can increase the delta negative charge over oxygen atom, but since in chloroacetic acids the chlorine is directly bonded to the CH2 group, which is directly bonded to COOH, the strong minus effect of chlorine withdraws electron density to a greater extent so that the electron density transfer to the positive oxygen is lesser than that in formic acid. So here hyperconjugation actually increases the electron density over the oxygen atom of the CO group, but since the position of chlorine is on the alpha carbon, its strong minus effect will absorb or take up or withdraw the electron density from the negative oxygen towards itself to a major extent, so that its acidity is greater than that of formic acid. When we come to alpha chloropropionic acid, the inductive effect of methyl group is very much small, neglected when we reach this carbon, and chlorine shows a strong minus effect. And again we should understand that chlorine is much more electronegative than carbon. Chlorine electronegativity 3.2 and that of carbon is 2.5. So even though there is one hyperconjugation canonical structure, the withdrawal of electron density from the negative oxygen, partially negative oxygen by the chlorine chlorine occurs to an appreciable extent, so that the electron density given to delta positive oxygen by inductive mechanism is less than that in the case of formic acid or chloroacetic acid. Say chloroacetic acid having a pK value of 2.867 and alpha chloropropionic acid having a pK value of 2.84. This lower value indicates that it is a slightly more acidic acid than chloroacetic acid. So there is a very small difference here, and that may be attributed to the position of chlorine and again the position of chlorine is alpha here, then which is the deciding factor between these two compounds. It is the hyperconjugation involving these two hydrogen atoms. There is only one hydrogen here, and these two hydrogen atoms with their CH bonds donating electron density to the carbonyl oxygen. The carbonyl oxygen here will be having a higher magnitude of negative charge than the carbonyl oxygen here. So the small acidity difference between these two is attributed to the hyperconjugation, higher extent of hyperconjugation in chloroacetic acid than in alpha chloropropionic acid. So we should suggest various electronic effects in proper directions to account for the variation in acidity of carboxylic acid. Now coming to another part. Consider the formation of hydrogen molecule. Now the potential energy or free energy diagram for a formation of hydrogen molecule is like this. Now here we have two hydrogen atoms with a potential energy shown by this point. When these two hydrogen atoms approach each other, the distance between the hydrogen atoms decreases along this curve. As the distance decreases, the potential energy also decreases. So at this point the potential energy is given by this point. At this point on the curve the potential energy is a lower value, and at this point the distance is large, and at this point the distance is small. So as these atoms approach, what happens is that the electron of one atom attracts the nucleus of the other atom, and the nucleus of the other atom attracts the electron of the first atom. So attraction causes a decrease in potential energy, and the distance between the atoms decreases. And when the atoms come closer, at a particular point we get a minimum distance, and that Distance denoted by R is the bond length. Now, we found further decreasing the distance, there is repulsion occurring between the nuclei of the atoms and the electrons of the atoms, so that the potential energy increases abruptly. Now you consider this portion alone. We find that as distance increases, potential energy increases. As distance increases, potential energy increases. So conversely, we can say as distance decreases, potential energy decreases. So in a bonded atom, as the bond length increases, as we stretch the bond, the distance increases and the potential energy is increasing. Now this can be compared to a small piece of elastic rubber bands. You hold the ends of the rubber bands and stretch it. Then we are supplying our energy to the rubber bands, and on stretching the length increases and the energy supplied to the rubber band is kept as its potential energy. You again stretch it, the energy supplied increases, the length increases and the potential energy increases, and you can stretch the rubber band to a point at which it breaks. So as bond distance is increased, potential energy or free energy increases. That is the main point here. Now consider the reaction between a molecule called benzyl chloride. Benzyl chloride is C6H5CH2Cl. Benzyl chloride reacts with the sodium hydroxide solution to form what is called benzyl alcohol. Now during this reaction, first of all, the bond between CH2 and Cl increases in length, or the bond is stretched during the reaction. Now during stretching, we have seen that potential energy increases, and since chlorine is more electronegative, during stretching or lengthening of the bond, the electron pair will be shifted towards chlorine. So it is a heterolytic process starting, and a delta positive charge will be created over the CH2 group carbon and a delta negative charge over chlorine. Now this delta positive charge developed on CH2 carbon can be stabilized by resonance. The broken arrow shows here that a part of the pi electron density is transferred towards the CH2 group. So we get a partial bond here and a partial bond here, and the partial positive charge on carbon of the CH2 is transferred to the position here, and this position in benzene is called ortho position. Now this point is called para, and this point is called meta. Now this partial positive charge can be migrated to para position by shifting of the pi electron here. Now one thing to remember here is that the arrow starts from this bond. This means that this is a pi bond and this is a sigma bond. So we assume that the upper bond is a pi bond. Then shift here occurs, shown by a broken arrow, so that part of the electron density of the pi bond is shifted in this direction, so part remains here, and we get another structure. So part of the electron density is shifted in this direction. This pi bond is partially broken and forms a partial bond here, so that a partial bond here and a partial bond here, we get delta positive charge at the para position. Now this continues, so that this bond partially forms a bond here. So this bond is partially shifted to the position in between these two carbons, so that remains a partial bond as shown here and a partial bond here, and the positive charge moves to the other ortho position, and we get delta positive charge here. Then finally this partial bond may shift in this direction, so we get partial bond here and the delta positive charge comes here. So delocalization of the positive charge, and that is again due to delocalization of electron, and there is it's a extended conjugation because this carbon is also involved in resonance, so that the length of conjugation, the length of movement of electron pair increases from 6th to 7th carbon, so that there is a decrease in potential energy. Now as the bond stretches, increases its length, the amount of positive charge over the alpha carbon increases and the amount of resonance increases, extent of resonance increases. So when the bond is gradually getting stretched, the magnitude of positive charge over alpha carbon increases, and during stretching potential energy increases, but as the magnitude of positive charge over alpha carbon increases, the extent of resonance increases, and as the extent of resonance increases, the potential energy decreases. So there are two opposing forces. The resonance tries to decrease the potential energy of the system. The increasing resonance tries to decrease the potential energy of the system, but the increasing length of the carbon chlorine bond tries to increase the potential energy. So as the lengthening of the bond increases, stretching of the bond increases, the amount of positive charge increases and resonance increases, so that at a particular point the potential energy decrease due to resonance, increasing resonance, becomes equal to the potential energy increase due to stretching or lengthening of the bond. So a point is reached when the partial positive charge over the alpha carbon or the CH2 carbon, this is the alpha carbon, the partial positive charge over the alpha carbon is sufficiently high that there is higher resonance occurring and the potential energy decreases to such an extent that it becomes equal to, the decrease becomes equal to the potential energy increase due to stretching of the bond or lengthening of the bond. This particular point at which the potential energy decrease due to resonance becomes equal to the potential energy increase due to stretching of the bonds is called a transition state. Transition state. So a diagram can be drawn by plotting potential energy or free energy, which are equivalent or proportional, and the progress of the reaction, the forward direction progress. The reaction proceeds in the forward direction. We study the progress of the reaction the forward direction. Then from the reactant here, that is benzyl chloride, the potential energy gradually increases because there is stretching, and gradually resonance also increases, and a point is reached at which the potential energy decrease due to resonance is exactly equal to the potential energy increase due to stretching or lengthening of the bonds, and that is called a transition state. Transition state 1 is drawn here. This is only an approximate picture because we have to show resonance also here. Now the magnitude of positive charge decides these aspects. So the magnitude of positive charge is such a value that there is greater resonance, and this becomes high enough to equalize the potential energy decrease due to resonance to the value of increase in potential energy due to stretching of bonds. Now, on further stretching of the bonds, the fractional positive charge increases to such an extent that the potential energy decrease due to resonance become more than the potential energy increase due to stretching of the bonds. So once again, the potential energy decrease due to resonance become more than the potential energy increase due to stretching of the bonds. So the decrease in potential energy has a higher magnitude than the increase in potential energy. So the net effect is a decrease in potential energy of the system. So stretching goes on, and resonance gains upper hand. Resonance increases gradually. The delta positive charge increases from say 0.7 to 0.8 to 0.9 and so on. So the extent of resonance increases, and ultimately we get the dissociated ions, that is benzyl carbocation and chloride ion. So at this point we mark it as I, and that denotes an intermediate. An intermediate is a species having sufficient stability, but still it is unstable because its potential energy is high. So it is more stable than a transition state because its potential energy is lower than that of the transition state. So an intermediate is a somewhat stable species formed during a reaction. A carbocation can be an intermediate. It is not so stable, but it is sufficiently stable than the transition state. And so during reaction, during the progress of reaction, we can isolate these intermediates, and its properties may be studied. Now the benzyl carbocation is the intermediate here. Now in the second stage of the reaction, the benzyl carbocation is attacked by a hydroxide ion. Now when a benzyl carbocation is attacked by a hydroxide ion, there again initially a transition state is formed. The formation of a bond is the reverse of breakage of a bond. Here the bond breakage passes through a transition state. When benzyl carbocation reacts with a hydroxide ion, then The reaction, that is formation of bond between benzyl carbocation and hydroxide ion, will also pass through a transition stage, and finally the product will be reached, that is benzyl alcohol, that we shall discuss in the next video. Thank you for attending me.